Hello, this is Learning Plan 3, Symbols and Diagrams. In this learning plan, we're going to learn the various symbols used in electrical schematics and diagrams, difference between each. The objectives of this learning plan are: identify the differences between pictorial drawings, schematic diagrams, line diagrams, block diagrams, and flowcharts. Identify the difference between the switch symbols, normally open, normally closed, normally open held closed, and normally closed held open. State the 5 basic components of a basic electrical circuit. Understand how to draw a circuit using symbols that illustrate the 5 basic components of an electrical circuit. Explain the difference between a manual control circuit and an automatic control circuit. Explain what a solenoid is for and draw the symbol for a solenoid. Define contactor. Give an example of its usage and state the 2 types of electrical contactors. Define magnetic motor starter and give an example of its usage. Explain how prints are read and how they are used during troubleshooting. We'll start off with pictorial drawings. A pictorial drawing shows the physical details of components as seen by the eye. In these slides, you're going to see a bunch of pictorial drawings to depict various electrical objects. Now, most often than not, you will not see a pictorial diagram in your workplace. But for teaching purposes, they serve a very good purpose. Symbols. Symbols are used to conveniently represent electrical components in diagrams of most electrical and electronic circuits. So on the right of the slide here, you have a bunch of various electronic and electrical symbols and a pictorial drawing to represent them. So if you look at the very top of the page, you see a battery. This is how a battery is represented in electrical schematic. If you have an AC power source or alternating current power source, it's represented with a sine wave with a circle around it. Okay, thermocouples are represented with this symbol here. Electrical conductors, very simply, they're the lines in your diagrams. Okay, when a wire is connected, it has a dot, meaning there's a connection there. If a wire is not connected, it'll be the lines will just cross, or you'll see there will be a little bump over the crossing line. Ground. Anytime there's a ground in your electrical system, it's portrayed with a symbol such as this. Looks like an upside down Christmas tree. Photoconductive cells, so light sensitive cells, be represented with a contact looking thing inside with a circle around it with lights pointing at it. This is a common symbol you'll see in almost all of your electrical schematics. This is what a transformer symbol looks like. This is a pictorial diagram of a transformer. A switch, so it's a single pole, single throw, it looks like a light switch. It's represented like this. Then you have limit switches. Limit switches have different ways of representing them. So this is a normally open limit switch. Notice the line is on the bottom of the dot. This is normally open, held closed, meaning that in its normal position something is holding it closed, like a door or a gate. Notice the line is still on the bottom. A normally closed limit switch is always drawn with its line on the top. Notice down here, normally closed held open, it's on the top, but it's not in contact with the dot. Contactors are represented much like this. Magnetic motor starters. Here's the contacts for a motor starter, and here's the motor starter connections. Motors. We have various ways of representing motors. So this is a single phase, single or dual voltage motor. See, there's 2 wires going into it. These are very common in your electrical schematics. If it's single phase, 2-speed, single voltage, you have high speed, low speed, and a common. That's how this is represented. If you have a 3-phase, single or dual voltage, Y connected or delta connected motor, it's always represented this way on a schematic diagram. A circle with 3 lines coming out at T1, T2, and T3. And different switches are represented in different ways. A foot switch looks just like a regular switch with a little elbow on top of it. Disconnect switches are represented this way. Anytime you see a dashed line in a symbol, that represents that something is connected. So each of these 3 devices are connected. This indicates a 3-phase disconnect. Lamps in a schematic diagram are always indicated with a circle with what looks like lights coming off of them. Bell, horn, buzzer, and a solenoid. Those are all symbols for electrical diagrams. Okay. A fuse is represented with what looks like a backwards S. Okay, again, pictorial diagrams on the left, schematic diagrams on the right. A circuit breaker looks like this. A diode, don't really have to worry about that too much, but yeah, we'll just skip these here. Okay, wiring diagram. The location of a component is generally shown as close to the actual circuit configuration as possible. So if we look at this diagram here, this is representing a waffle iron. Okay, so we have our 120 volt plug that would plug into a wall outlet, going to a switch or the on-off switch. Going through here, this is what we call a temperature switch. That goes through. These resistors represent the heating elements in the waffle iron. Then back to our source. Okay, so that's a wiring diagram, and it's representing this pictorial up top. Schematic diagrams are essential in troubleshooting because they enable an individual to trace a circuit and its functions without regard to the actual size, shape, or location of the component, device, or part. Okay, so this is a schematic diagram of the exact same waffle iron on the last page. We have a switch, temperature switch, resistors representing heating elements, and then we have our power source. So it's just another way of representing the same thing. A ladder diagram or line diagram consists of a series of symbols interconnected by lines that are laid out like rungs on a ladder to indicate the flow of current through the various components of a circuit. One-line diagrams use single lines and graphic symbols to indicate the path and components of an electrical circuit. Okay, so there's a single path of an electrical circuit. Very useful in troubleshooting machinery because you can just trace the path, find out where your problem is. All electrical circuits include the source or power source, a load, a control device, and conductors. Every circuit must have these components. Most circuits also include fuses or circuit breakers to provide protection for the circuit. Okay, so you must have a load, you must have a control device, which is represented by the push button here. You must have a load, you must have current carrying conductors. You can also add fuses and circuit breakers. A line diagram may be used to illustrate a manual control circuit of a push button controlling a pilot light. So if we read this diagram, it's a very simple diagram. We can see our transformer is here. Our transformer is stepping down our voltage, which is what a transformer does, to 24 volts AC. Okay, so power is coming to here. When we push this push button, current flows through the push button into our light, out of the light, back to our source. The light is then illuminated. Okay, a line diagram may be used to illustrate the control and protection of a single-phase motor using a manual starter with overload protection. So we have a manual starter contact here. We have a motor. Oops, excuse me. And then we have our overload contacts wired in to protect our motor. Okay, so that's a line diagram. This is a pictorial diagram. Electric motor on a sump pump can be turned on and off by using an automatic control device such as a float switch. So in this case, what we have here is an AND circuit, meaning this manual starter must be turned on, contacts closed. This float switch must also be closed and our motor will run. Normally closed contacts of a float switch may be used for a pump operation to maintain a certain level of water in a livestock tank. So this is an example for using a float switch. A float switch is a device that floats on water and basically opens and closes electrical contacts to allow a motor to run or not run. In this case, the switch or the manual contactor is turned on. When the float gets to a low enough level, or water gets to a low enough level, contact close, run the motor, fills the tank back up. When the tank gets back up to a certain level, contact opens and shuts the pump off. A solenoid is an electric output device that converts electrical energy into a linear mechanical force. Here's a symbol for a solenoid. Here's a pictorial drawing. So a common application for solenoids is to control a door lock that is open only when a push button is pressed. So it might be a manual lock here to not allow people in a room. When a push button is pressed, solenoid is energized, unlocks the lock, door can open. A contactor is a control device that uses a small control current to energize or de-energize a load connected to it. So a contactor is a device that uses small current to control larger current. The electrical operation of a contactor can be shown using a line diagram, pictorial drawing, and or a wiring diagram. So what you have to realize with Greenheck, they have a combination of line diagrams and wiring diagrams. So I'm going to kind of put these two together to see, hopefully, see if I can help you understand this. When I push PB1 here in this line diagram, that energizes this coil. This is the low voltage side of the coil. Energizes this. When this is energized, the contactor pulls in, we say. It closes its contacts. Okay, so C1 closes these contacts, which then turn our larger power or larger power source on, or connects it to our load. So a line diagram, push the push button, energize this coil. When this coil is energized, it closes these contacts, connects this power to our load. Auxiliary contacts are part of a electrical contactor. They may be added to a contactor to form an electrical holding circuit. So I'm going to zoom in on this circuit right up here. This circuit here is what we called a holding circuit, latching circuit, memory circuit. That name is synonymous for this diagram. How this works, we have our power source L1 and L2. We have a stop push button, which is normally closed. Current flows through the stop push button to start. Now this is normally open, so in its normal state it's not conducting. We push this push button, current is allowed to flow to our contactor, which energizes contactor C1. Okay, the path continues to L2. When C1 is energized, it closes its contacts. So C1 is energized, any contacts associated with it or attached to it close. We have C1 auxiliary contacts here. So when this motor starter is energized, or when this contactor is energized, these contacts close. Now if I let go of the start push button, we have an alternate path. So essentially this contactor is keeping itself running. Now if I push the stop button, it breaks the path of current flow, de-energizes the contactor. When this de-energizes, this contact opens up and it shuts off. A motor starter is essentially a contactor that includes motor overload protection. So you have overload protection in case a motor is overloaded. Electrical operation of a motor starter can be drawn using a line diagram, a pictorial drawing, and or a wiring diagram. So again, I'm going to zoom in here. We have same circuit we looked at in the last slide. We have M1, but now we added overload protection. So let's go over this again. When I push the start button, current is allowed to flow to M1. This is a normally closed contact, so current flows through to L2. Now when M1 is energized, it's going to close this contact, keep itself energized. But now say your motor is running in a high ambient temperature, or it's running slightly over its rated amperage. These overloads are designed to protect the motor against those situations. So if a motor is running for a period of time over amperage or in high ambient temperatures, these overload contacts will open, breaking the path of current flow, stopping our motor starter, which stops our motor. So print reading. Print reading is a term it requires understanding the relationship between a component symbol and the physical shape and location of the component. So that's kind of why I was going through this exercise, pointing out the symbols and what they actually look like in real life. You'll get a chance to actually do an exercise to understand the relationship between a symbol and actual physical components that you'll be installing in a panel. Troubleshooting requires reading a print, so you must know how to read the print to determine the location and use of individual components and understanding how to use test equipment. So an understanding of the test equipment that you learned in previous learning plans and being able to read the prints that you're using are essential for troubleshooting problems with your machines. That's the end of Learning Plan 3, Symbols and Diagrams. Thank you. Have a good day.